Symmetry Festival, the opening session. I want to apologize for the rector of the UNESCO Institute for Hydrological Education. He could leave for the United States for a conference, so he cannot give a welcoming speech to you. I do not want to tell too much. I am very happy that we gathered here, and thank you all for coming and join us at this event. This is the fourth Symmetry Festival in a series during 10 years. Let me introduce first the chairman of our this morning session, Larry Good of the Hartford University, and he will introduce you the lecturer of this morning session. Before I give the floor to Professor Good, let me tell you a few technical information. So we will have 3 morning sessions today on Monday and Tuesday in this room. All the other sessions, that means all the afternoons and the morning sessions tomorrow and on Wednesday will be at the UNESCO Institute of Hydrological Education, which you find easily in a 15 minutes walk from here, in the heart of the city, Delft, and the exhibition, Symmetries, the 100 will be in the neighboring building next to the UNESCO IHE, and the opening ceremony with a small reception will be held this evening at 7 o'clock. You can take lunches at the cafeteria of the UNESCO building. You are offered a very cheap lunch there. You can make your choice and pay yourself either by card or in cash. Tomorrow the cafeteria will be closed, but in the building next to the UNESCO building, in the same building where the exhibition takes place, is another cafeteria, and you can have your tomorrow lunch there. As regards the Sunday program, we will meet in the morning at 10:15 at one of the tram stations. I will announce it tomorrow, and we will take a tram to the city of Hague, where we visit together the Escher Museum, and after lunch we will get back to Delft, and we'll have the family day programs at the main market square of Delft. We hope very much that there will not be raining. In the case of rain, we will move to the exhibition space, and that is a large space where we can organize the workshops. So, let me invite Larry to introduce the speakers for this morning.
Fortunately, I don't have to hook this up. I'm the chairman of the executive board of the International Symmetry Association, and I'm also a physicist, so I take pleasure in introducing Professor Gerard de Hooft. A little bit background. About a half a century ago, physicists were trying unsuccessfully to accurately describe the nature of the interactions between elementary particles, such as neutrons, protons, electrons. Many promising attempts to do so were the theories that followed the lead from a 1954 idea by physicists Yang and Mills. But when detailed calculations were attempted, infinities resulted in those theories. And you can't calculate with infinities. Then came the breakthrough. In 1970, Gerard de Hooft who was working on his PhD with his thesis advisor, Martinus Veltman, found the method to determine which theories can be renominalized, in quotes, and thus which theories can become, so to speak, infinity-free, and how the so-called Higgs particle figures in. For that work, Professor de Hooft and Veltman were awarded the Nobel Prize in Physics. For 1999. One finally had, as the Nobel Prize poster says, a theory to reckon with. Reckon means to calculate with. Difficulties. Excuse me. Professor de Hooft, who has been honored by scientific societies from around the world, continues to be actively engaged in a variety of research areas, including quantum gravity and black holes, and fundamental aspects of quantum physics and their implications for superstring theory. In addition to his many research papers and talks, he has also published several books, technical and popular, including Introduction to General Relativity, Under the Spell of the Gauge Principle, and In Search of the Ultimate Building Blocks. I should also mention that he has an asteroid named after him. It travels within the space between Mars and Jupiter. If you're interested, look under 9491 to Hooft, and there's no apostrophe before the first T in this case. On behalf of the International Symmetry Association, it is a great pleasure for me to introduce Professor Gerard de Hooft, who will speak on symmetries in elementary particle physics. Professor de Hooft.
Thank you very much. I'm holding the microphone right now. Okay. So yes, I was asked to talk about symmetries in particle physics, assuming that there is any. Well, that assumption is not only correct, but I should add immediately that symmetry plays a very central role in understanding the very tiniest units of matter, subatomic particles. We can't understand them without first understanding which symmetry principles they obey. In fact, symmetry always plays an important role in all of our understanding of the physical laws. That varies from the behavior of solids and liquids and gases to the behavior of the tiniest particles in the universe, but even the universe itself. So all these are controlled by symmetry principles. And I can even add that one step further. The symmetry principles allow you to understand all the dynamic rules. Particles interact. If two particles come too close to each other, they might undergo some sort of interaction. They might collide, or they might run through each other. They might transform into other particles. But all this is controlled by laws that you only understand if you understand, first of all, which symmetry principles these particles obey. So that means that I could discuss all of elementary particle physics here, but that would be too much for one talk. So there's a lot of symmetries, and I will skip quite a few very important ones just because I have no time. Maybe in the end, if I discover that I talked faster than I expect, then I might mention even some more symmetry principles that also hold in particles. Well, we are here in the building of architecture, so it's only appropriate to take one of the marvels of architecture, the Taj Mahal in India, and discuss its symmetry. And then I want to explain to you in what way we think of symmetries in particle physics. This talk is going to sound at some point rather technical, and you might be surprised. You know, symmetry is just a thing of beauty. Symmetry patterns are everywhere, certainly in architecture. And you might think they're only there to please the eye, but they play a much more important role than just pleasing the eye in physics. So what is a symmetry? And here I want to agree, first of all, what we mean with a symmetry. There are two aspects, two steps that you have to make. One is you have to have the notion of a transformation. What is a transformation? Well, consider any situation that you might have in a physical system, and then replace that by some other situation by making a simple operation, like rotating things for 90 degrees, or take a step to the side, or take a step to the future, or a step to the past, or make some other change. Think of this room and let everybody sit somewhere else. That is a transformation. The transformation goes to a certain room. And the transformation that's important for this building is to flip it over. So I'll first make the transformation. So here I have the same building, but I allow it to mirror it. So the mirror is a device that allows you to look at the system after it was transformed into its mirror image. So here you see the same picture as above in mirror image. And now you have to do something else. You flipped it over, you made this mirror image, and now what? Well, let's now compare the top picture and the picture below and look at the differences and similarities. The first thing that strikes the eye is the similarity. The two pictures look nearly identical. That's a statement that this building has an important mirror symmetry in it. But when you look more carefully, you will see the differences. For instance, the trees growing there, they don't care about the symmetry, they violate it. So there's on the top picture, you see a tree on the right, and that same tree sits on the left in the picture below. So that tree spoils the symmetry, you could say. And there might be other slight differences. For instance, the way the thing is illuminated by the sun. Well, the sun was at the left on the top building, no, at the right on the top building, it's at the left on the building below. So the sun shines from a different direction, and that you notice as a subtle difference in the pictures. But as architects, you probably realize that the symmetry cannot be perfect. There will be paintings and tilings in this building which are not symmetric. The doors may open in a different way on top and below. So, of course, there are other subtle features that violate symmetry. So here it is, and this we have in physics also. You have a transformation. After the transformation you compare. You say, well, 99% of the two images is the same, but 1% is different. And sometimes that's 10%, sometimes that's nearly 100%, which means that the thing is not symmetric at all. And sometimes the symmetry is absolutely perfect. Also that may happen in physics, that the symmetry is so perfect that you see no differences at all. So this is what we mean with symmetry. And remember, this is also always how I talk about symmetry. And that means sometimes the whole idea becomes rather technical. This is a simple example of a matchbox, and a matchbox is easy to demonstrate rotation symmetry. I can, if this works, but it's always a bit difficult. Let me see if I can make it, no, this thing here. This is what I want to do. This is a rotation about a vertical axis, and then I might go on, and if all is well, I'll make a rotation around a horizontal axis. And I had more pictures of this sort, but I found that the computer is not good enough to make this predictable, so sometimes a picture does something else than I want. So what I want to show here is that the matchbox can be rotated around the horizontal axis, around the vertical axis, and you can compare what happens after rotation. And you'll agree that this matchbox sits in a different position, say the right away, from the previous one. So in the matchbox, the symmetry is rather badly broken, although the angles are located in a similar way. Now there's something remarkable to be said about this matchbox, about these two rotations around the horizontal axis and around the vertical axis. And what's remarkable is if you perform two successive transformations, the result may depend on the order. I don't know whether you knew this. If you take a matchbox, you first rotate it one way, and then say rotation A, which means a rotation around a vertical axis by 90 degrees to the left, say. And then you say another rotation is a rotation around the horizontal axis by 90 degrees, clockwise or anti-clockwise. So you have a rotation A and a rotation B. Now I take two successive rotations. Now for the matchbox, it now depends in which order you do the successive rotations. If you first rotate around one axis, then the other, you don't get the same thing as if you first rotate around the other axis and then the previous rotation. The rotations are exactly the same, but the order is different, and then the result of it is different. And that gives the notion of symmetry already the first fundamental complication that makes it interesting physically and mathematically. So mathematicians know how to call this. They say this is a non-abelian symmetry. So Abel was a well-known Norwegian mathematician, and as a mathematician he studied the rotations and other symmetry groups and found that some symmetries are abelian, that's what we call it now, and some are non-abelian. And non-abelian, it depends, the result of two rotations depends on the order. And that has very important consequences, particularly in physics. As for rotations, there are also rotations without all angles. And the most perfect object regarding rotation is a sphere. The sphere is, by definition, the object is completely rotationally invariant. No matter how far, over how many angles you rotate, what angles you rotate the sphere, it always looks exactly the same, except for the light shining on it, as you see here. So in physics, the sphere is a prototype of a perfectly rotationally invariant object. But remember, life is not that simple. In physics and mathematics, you can consider spaces with different numbers of dimensions. So if I took a sphere just in 2 dimensions, it becomes a circle. It's a perfect symmetrical object. But in higher dimensions, you get higher dimensional analogs of the sphere. And those are very fundamental properties. Now, elementary particles can be like spheres, but they don't have to be perfect. And in fact, indeed, some elementary particles deep inside the atomic nucleus have perfect spherical symmetry. So in all respects, you consider them as little marbles with no angular features at all. But many particles are not like that. So molecules, for instance, and other particles, they're often not like that. But also, very simple particles like the electron are not like that. You might have thought that the electron is a perfect sphere, but it isn't, because these particles rotate. And they have what we say angular momentum. I'll return to the concept of angular momentum very soon. But you see, these are soccer balls, and they're just familiar objects. But you notice, although they have nearly perfect spherical symmetry, they can rotate, they can show spin. And spin, as you might guess, is an elementary property of subatomic particles. Most particles spin in some way, some direction or another. And as soon as a particle spins, it loses some of its spherical symmetry because it spins around some axis, and that axis can be oriented in different directions in space. So think of when you play tennis and you get a spin effect to the tennis ball, then it might follow a curved trajectory. But of course, the direction in which the trajectory turns depends on how you make the ball spin. And that gives the particle some sense of direction. Whenever you do experiments with particles, small particles, large particles, it doesn't matter, they always spin. In astronomy, you have planets and stars and galaxies, and all have the property that they always spin around. They are never completely motionless, or rarely so. This is a very central property and is directly related to the symmetry of rotations. So we call symmetry rotation a symmetry, and then the next feature is spin. Now, so far I've mainly showed as a simple example the rotation, but there are other symmetries, and one symmetry is called translation. Translation means I make a step to the side, I make another step to the side, I can go on like this, and then and then what do? Well, I compare the new situation with the old one. Is it symmetric or not? Well, I am not. I'm standing somewhere else, and you recognize that. So my body is not translation invariant. But here you see a street with all identical houses. If I make one fundamental step to the right and the left, you find to get the same pattern back. So this sequence of houses has an important symmetry. We call it translation symmetry. If I make one step from one house to a neighboring house, and I make that step everywhere, I get the same situation back. So this picture is asymmetry. And remember, I make a transformation and I compare after transformation, I compare the situation with what it was before. Now these symmetries in physics play an important role in understanding dynamics because symmetry plays an essential role in motion. When you have motion, you might have that something moves. So this car moves with a certain velocity to the right, and motion, of course, can only be regarded, well, it has some peculiar features as soon as there's a symmetry involved. And so the moving car relates to translation symmetry in the same way as a turning ball or a working clock has its rotation symmetry. I want you to remember that because this returns many times. Now there's a very important law when you think of dynamical objects, of systems obeying mechanical laws. The laws of mechanics were formulated by Isaac Newton for the first time very accurately when he discovered that you can understand why planets move in elliptical orbits around the sun. He understood that and he wrote down the very elementary laws of mechanics. How does an object react when you push it in a certain direction or when you pull it? A planet is being pulled towards the sun by the big gravitational attraction from the sun. As a consequence, the planet doesn't move directly to the sun, no, it rotates around the sun in orbits. And Newton could compute those orbits. And he had some fundamental laws there, and then mathematicians went to study those laws, and what they found is that there's some peculiar relation between symmetries and conservation laws. There was a female mathematician, Emmy Noether, who discovered what we now call the Noether theorem. The Noether theorem has it that whenever you have some mathematical system with a symmetry in it, then there is a conservation law. Now, the laws of gravity remain the same if you rotate an object. That's illustrated by the planet Earth. The planet Earth is merely a perfect sphere. And that is because the gravitational laws that control the shape of the Earth are rotationally symmetric. So if I travel over the Earth, that's the same thing as rotating yourself with respect to the center of the Earth around a certain angle, but you find that the gravitational force is practically the same. What violates this symmetry is the fact that the Earth also rotates. It has a rotational axis. And due to that axis, the Earth is not a perfect sphere anymore, it flattens a little bit. But quite generally then, when you have rotation as a symmetry for your laws, you have a conserved quantity. And in the case of planet Earth, that is angular momentum. The fact that the Earth rotates around its axis once every day, roughly speaking, means that there's something conserved. The Earth can't just start to rotate faster or slower. And that is understood by Newton as a consequence of his laws of motion. You can only make the Earth rotate faster or slower if somehow you can exert a force on the planet Earth. Such forces do exist, so the Earth is not absolutely constant. Billions of years ago, the Earth rotated much faster than it does now, because the Moon has certain forces on the Earth which makes it rotate slower. That's a very delicate mechanical effect. If you ignore that, the rotation of the Earth is constant. And that's the law of conservation of angular momentum. Sometimes in popular physics books, this law is illustrated by someone who is skating or a ballet dancer or someone, and you rotate yourself around your axis as fast as you can, and suddenly you pull your arms together. Then what happens is the moment of inertia changes, and then as a consequence of conservation and momentum, you start to spin faster. At least the eye thinks that you spin faster. Actually, the angular momentum remains constant. So angular momentum is a very important consequence of rotation symmetry. And so this is how symmetry plays a very central role. In everything that rotates, well, nearly everything does rotate in the universe of physical objects. But it doesn't stop at rotation. You can look at translation, and then we observe quantities called momentum. Imagine a train going over the rails, and the rails are horizontal, and the physical properties of the train remain the same when it moves over its track. And because of that, the train has a conserved property, and that's called momentum. That's mass times velocity. The product of mass and velocity of a moving object is practically constant due to the translation symmetry of the laws of nature that forces it to go. So that's why if you have a moving train, it will be difficult to stop the train unless you pull the brakes very hard. Or to accelerate the train, you need electricity to have this engine on so that the train accelerates. If you don't do anything, the train will just keep practically constant speed. That's conservation momentum. It has to do with the fact that laws of nature remain the same if you translate things. So my biological system remains the same when I'm walking. My heart doesn't go faster or slower when I replace myself. That's called conservation of translation, symmetry in the laws of nature. But you can also consider mirror symmetry. Now this is a more subtle one, because the mirror is only a flip-flop transformation. You can only make one mirror transformation. If you do it again, you get back to the original. Well, that's also associated with conserved quantity, but that's typically a property of the subatomic particles. All the particles have a quantity which is either +1 or -1. If you take two particles together, it has this property -1, it goes +1 again. That property is called parity, and it is directly the conservation law that is associated with mirror symmetry. So a famous particle, subatomic particle, next to the ones which are known, well, more or less publicly, but a more difficult particle is a pion. The pion is a particle whose wave function is negative on the parity. So if you look at the pion under a mirror, you find that something switches in the pion if you mirror image this object. Another very interesting symmetry transformation, which I mentioned very briefly, I'll mention it again, is translation in time. I can look at the system now, and I can look at how it was a second or an hour ago, and how it will be a minute or a year later. And this is called time translation symmetry. Laws of nature don't change if I go forward or backward in time. That is again associated with a quantity which is conserved, and that quantity is called energy. So energy, in the physical sense, physical energy, which is for a moving particle, it's 1/2 times the mass times the velocity squared. That property is conserved because laws of nature don't change over time. If the I changes over time, the energy will not be conserved. So, for instance, if I would shake this thing, but I'll have a periodic change there in touching it, then I'm violating time translation event. I can add energy to this thing, such that if I do this many times, it will fall over. That's just adding energy by having time non-invariance. So if you see any object where energy is not conserved, you say, the laws of this object are not the same now than they were a minute ago. And this again is a central issue in particle physics. Now, physicists discovered that in the case of subatomic particles, the converse is also true. If you see a conservation law, no matter what, you discover there's a property of these particles which is conserved. The particle direct, this property doesn't change, then that is associated to a symmetry. So it goes both ways. There's a famous property among the subatomic particles when maybe 60 years ago or so, physicists discovered over 60 years ago, that some subatomic particles collide. They found new particles of a new type, strange particles. Strange particles will be produced when ordinary particles collide with very high velocities. And then physicists discovered you could introduce a concept, a notion called strangeness. How strange is a particle? Very strange, really strange. Strangeness can be positive or negative. And when two particles collide, they find that the total strangeness is conserved. A particle with strangeness +1, a very strange particle, can collide against a particle with strangeness -1, another strange particle, and then the result of two collisions is a particle with no strangeness at all, +1 with -1, 0, so then the strangeness might disappear. But once a particle has strangeness, it keeps that for a while. Eventually, the particle decays, so strangeness is not a perfect conservation law, therefore the symmetry is associated with that. I won't try to bore you with trying to give a mathematical definition of that symmetry is not a perfect symmetry of nature. And there are many other such examples in particle physics. So let me go into the atomic nucleus. Atomic nucleus is the point where most of the mass of an atom is situated. The atom consists of a nucleus with electrons going around it. Inside that nucleus, there are subnuclear particles. And the most conspicuous particles in a nucleus are the protons and the neutrons. So in this picture, I made the neutron green and the proton red. These colors, of course, mean absolutely nothing, because at such small scales, the notion of ordinary color doesn't work anymore. So colors are only there for notation purposes. And this is typical an atom with at least 8 or so subatomic particles in it. And all atomic nuclei have these particles. These protons and neutrons have a peculiar feature. So I made this picture before, I found the other one, so I have different colors, for which my apologies, but it means the same. You have protons and neutrons. Now, protons and neutrons resemble each other, in spite of the fact that the proton is electrically charged and the neutron is a neutral particle. But with that, I also indicated the most important difference between protons and neutrons. But more conspicuously is that in many other respects they are identical. For instance, their masses, where you see only 1 point in 1,000 is different. So the mass of these two particles is nearly identical. The neutron is nearly the same mass as the proton. It differs by a very tiny, but very accurately measured amount. The electric charge is different. Okay, the electric charge is different, but there are other interactions. The forces that keep protons and neutrons together in the nucleus are very, very strong, much stronger than the electric forces. Therefore, in spite of the fact that these charges are different, the particles behave practically identically inside the atomic nucleus. So now I can imagine a transformation under which the laws of nature change very little in an atomic nucleus. And that transformation is to replace the proton by the neutron. So I'll do this and ask, what are the similarities and what are the differences? Well, electric charges are different, because the interchange proton and neutron, so these two systems have different electric charge. But the mass is the same, the mass distribution is the same, and the forces that they exert on each other and other particles are nearly identically the same. So many things do not change if you make this transformation. Then we say this is a symmetry of the laws of nature. Now, it so happens that mathematically, these things are more complicated than I have just said by words. You can interchange protons and neutrons, but actually you can do something smarter than that. You can say that this interchange is due to a rotation in some internal space. Again, I'm not going to fatigue you with trying to explain that mathematically in more detail, but the interchange operation protons and neutrons is part of a larger set of operations which correspond to rotations in some sort of imaginative space. Not ordinary space, but what we call isospin space. Why isospin? Well, if these things can be replaced by such a transformation and they rotate, it means that there is a rotation property called spin. But now it's spin in some internal space. We call it isospin. Iso comes from the Greek isos, which means similar or resembling. So it's a space resembling ordinary space. The mathematical laws and rules are the same, but it's an internal space. You don't see it directly. It's a space you get if you try to interchange protons with neutrons. And the spin in that space is conserved. So there's an important conserved quantity called isospin. And that isospin can be measured for particles, and you can discover it is conserved. By imposing that conservation law or laws of nature, you made a very important restriction, and it allows you to actually formulate what the laws of nature will be like for these particles. So you can do a lot with these with these principles. It looks simple. Well, you also notice that I skipped some mathematics, so it's not that simple anymore. But once you have these simple principles, symmetry principles, you understand already a little bit about the forces between protons and neutrons. I just said before, the forces remain the same, but it's not as easy as said than done. You have to write down the equations for these forces. And to make these forces stay the same if you rotate in isospin space, well, that means you have made a very important restriction on how these forces can act. And by studying this, you already have learned something. But this is only the beginning. I'm going to do something much more complicated than that. I'm going to consider not one proton or one neutron which interchange. I take thousands of them in different spots in space and time. So here you have, well, in 3 locations in space time, I have a proton and a neutron. And now I'm going to make this interchange, but I'm not going to make the interchange everywhere, but only in one location, only in one spot. I replace protons and neutrons, I'll show it again. So in one spot I replace the proton and neutron, but in other spots I don't. Is that a symmetry? Well, that's not quite a symmetry anymore of nature. Why not? Well, there's a law that says that when 2 particles are identical, they can't sit in each other's place. But when 2 particles are different, they may overlap each other. Now, if we interchange proton and neutrons in the middle, not the others, now the neutron from above can sit in the place where the original proton sits. Otherwise it cannot. So it's not quite so easy to see that the laws of nature will be invariant under this symmetry. That is this a symmetry or is it just a transformation that leads us nowhere? It turns out this is a very important symmetry. But symmetries of this sort are associated with fields. So now we get the notion of a field. A field is like an electric field or a magnetic field, but if you do this with protons and neutrons, we get the isospin symmetry, and the isospin symmetry is non-abelian. And now you get a field that just has electricity and magnetism, but associated with a non-abelian symmetry. And such fields are called Yang-Mills fields. When the chairman introduced me, he mentioned very briefly Yang-Mills fields. Well, Yang-Mills fields and forces turn out to be elementary forces in particles. Once you understand that, you already learn much more about the interactions between protons and neutrons and other particles. So you see that interaction is associated with the notion of symmetry. I make a transformation, I compare what happens, but now the transformation is this one, and compare what happens is not so simple. Now you have to say that also make an associated transformation in the fields, and those are the Yang-Mills fields. It turns out that those fields obey laws very similar to the laws of electricity and magnetism. Electromagnetism, in fact, is also based on symmetry, but again, I have no time to discuss the details of that. But Maxwell, when in the 19th century, he wrote down the laws of electricity and magnetism, he didn't realize that there was a symmetry associated, but very soon it was found out, yes, there are very important symmetries there. And once you understand the symmetries, you've understood 90% of Maxwell's laws. You only have to say symmetry as a rule, you get the laws. Same here. So C.N. Yang had already done his the work for which he later would get the Nobel Prize. That was on parity symmetry, the mirror symmetry of particles, finding that some particles are not only not equal to the mirror image, but interactions violates mirror symmetry. So mirror symmetry is not a perfect symmetry in elementary particles. And but Yang-Mills introduced a field that has the following property, that if you send a proton through such a field, the proton will turn into a neutron. Thank you. Okay. So, you remember I had the symmetry law that protons and neutrons are identical. Now Yang-Mills introduced a field such that the proton can go through this field and turn to a neutron. Or vice versa, if I do it the other, oh, what's happening? If I do it the other way around, then I can also turn a neutron back into a proton by going through that field. So, and this is sort of continuous transformation, that's why we have isospin space. Yang-Mills discovered that the equation of these fields is just like electromagnetism, but a bit more complicated. So complicated that people got confused about those fields, because the first thing you did was search for such fields in the laws of subatomic particles and found they aren't there. Yang-Mills are just having daydreams, but it's not the real world. it turned out that a lot more is happening, and to understand those young Mills fields, you have to understand some other things about symmetry. So this symmetry, it seemed simply not to be there in subatomic particles. But that was because people did not understand another mechanism, another feature, and now I come to a very important point of symmetry breaking. Symmetry, as I said already before, might not be perfect. But the reasons why a symmetry may not be perfect could be different. And one very important physicist, someone who played a very important role in the early days of physics, was a Japanese physicist by the name of Yoichiro Nambu. Nambu discovered that symmetries which are understood in condensed matter also holds for symmetries for the subatomic particles. So he understood a very important phenomenon that symmetries may undergo not only in material systems but also in elementary particles. And this is called spontaneous symmetry breaking. The symmetry can be broken, but the breaking can be spontaneous. Now what does that mean? And when he received the Nobel Prize just a few years ago, he had to wait a really long time, forget that, because this was in the 1950s and 60s that he made these observations. But he was some 90 years old, and he felt himself too old to give his Nobel speech. So his younger collaborator gave the speech, and he gave a very nice illustration of spontaneous symmetry breaking. He said, consider a vertical rod, a solid metal rod. And I put here 3 of them, but consider any one of these rods. These rods have nearly perfect rotation symmetry around their axis. So every rod has an axis, and if you spin the rod along that axis, you find that it nearly remains identical. So apart from a little surface reference which I drew here, these rods are symmetric on the rotations around their axis. They are symmetric, and it's also conspicuous that they are because they're perfectly straight rods. So now let's put them under pressure. So here comes a pressure on that rod. I take the middle rod and I push it. I push it so hard that it shrinks a little bit. And but it keeps its perfect rotation symmetry. But now suppose that the rod, although it's made of metal, it looks like that on this picture, is not that strong at all. I push too hard, it will start to buckle. And now the question is, in which direction will it buckle? When it buckles, it loses its cylindrical symmetry. However, the material out of which the rod was made would itself not allow any breaking of that symmetry. Also, the force doesn't break the symmetry. The force is directly in the vertical direction. So how and why does it buckle? Well, you feel as, in your daylight experience that will happen one day. If you push too hard, the thing will buckle. But in which direction will it buckle? That is difficult to predict. In fact, impossible to predict. It's just a preferred direction that the system takes, but in which direction, you don't know. And this phenomenon happens very frequently in the laws of nature. You find this everywhere, that if I put this microphone on its edge, like this, I can think that it's perfectly symmetric, but not it will fall in one direction. But in which direction, we don't know. That's the hard thing to predict. The easy thing to predict is that it will fall in some direction. And in the case of this rod, you can also predict how far it will buckle. And at some point, it becomes strong enough again, and it will go farther than that. This we call symmetry breaking, but it's spontaneous. That is to say, I did not put it in which direction it will buckle, but I get it out of my equation that it will buckle somehow. And this happens in many examples, and it was in particle physics by a guy named Peter Higgs. Actually, he wasn't the only one. At that time, there were other people who did the same thing, but Higgs made one more observation which made him put him aside for a moment. And the other guys, Engler and Brouwer, and actually there were more people around the time, all in the early 1960s, they noticed that spontaneous symmetry breaking plays a role in particle physics. Now this picture I took from another talk where I explain in more detail how spontaneous symmetry breaking works. And it's often illustrated by what we call a Mexican hat potential. Higgs himself prefers a wine bottle. Well, if you look at the center, at the bottom of a wine bottle, then you find there's a bulge in the middle. And you can try to put something on top of that bulge. So I call it a Mexican hat, and I put a particle on top of the Mexican hat. Well, I can put it there, but somehow you feel that that's not a very stable position for a particle to sit. It will fall down. So after a while, the particle will always disappear and go into the rim of the Mexican hat. Now, the whole situation was symmetric. Laws of nature were symmetric. Where in the rim will the particle go? Well, this is impossible to predict. It will go somewhere. But when it goes there, you also discover that there's a new symmetry, a new degree of freedom. The thing can rotate around in the rim of the Mexican hat. So when you have a spontaneous symmetry making, you get for free a possible way for things to rotate. You can now rotate this particle, and that gives you a new physical phenomenon. When you have spontaneous symmetry breaking, you get that you can make a transformation which costs no energy. And that's the rotation. And that means a new degree of freedom, and in our particle laws it meant a new particle. Well, in this case it was only that a particle could spin in a new way which it couldn't do before. But there was something else, and this was often not so much appreciated, that if you have this, you also get a new degree of freedom in that direction, in the radial direction. Now the particle can oscillate in its Mexican hat potential, and that oscillation is stable. It won't immediately fly out anymore, whereas the top was unstable. Now this position is stable, but that is also a degree of freedom, and that is associated to a new particle. And it was Peter Higgs who said that this, when you have spontaneous symmetry breaking in particle physics, you generate new particles that way. And this particle is now known as the Higgs particle. And the Higgs particle has played an interesting role in the whole history of particle physics, because we needed the Higgs particle to tame those infinities. When I was introduced by the chairman, he was surprised to mention infinities in particle physics. And you needed that Higgs particle, that other degree of freedom in the rim of the Mexican hat, to tame the infinities in the interactions. And not only that, we found that without Higgs particles we couldn't do it. And that is that the Yang-Mills fields were essential to understand the weak interactions, but the weak interactions had a nasty property that they also violated another symmetry property of particles, which I mentioned before, which is parent symmetry. The fact that if you look at the mirror image, you get the same. Well, what Yang, together with T.T. Lee, actually got his Nobel Prize for was the discovery that the laws of nature are not invariant on the mirror symmetry. If you look at some particles in the mirror, they don't look the same. Their interactions are different. But to get that in a Yang-Mills field is very hard. And that you can only do if you first try to have particles without mass, and then you introduce mass in a way that the mass comes out as a spontaneous symmetry breaking. And therefore this theory was going to have a Higgs particle. And that particle turned out to be very difficult to detect. So when the theories of weak interactions were clarified, a few decades later, the agent of the weak interaction, which is similar to a photon particle, was discovered in experiments, first in the United States and then later at CERN in Geneva. They found these particles and measured their properties. But this one particle, the Higgs particle, was elusive. That particle was too difficult to measure and to detect. So for about 50 years, this particle remained undetected. And only very recently, but in fact last year, in a beautiful, enormously large international experiment made in Geneva at CERN, this particle for the first time was detected and could be measured. And its mass could be measured to be 126 GeV. A very important result. Only now theorists are realizing that they could have predicted this mass if they understood the laws of nature better, because it's a very special value. And now we know what this possibly may be related to. It's very, very important and very new features. The field of this Higgs, in a way, allows us to distinguish particles from some mirror images. As I mentioned earlier, the electron and neutrino, oh, I think I forgot to mention, by the way, there's a proton and neutrons have isospin symmetry, but for electrons and neutrinos, it's the same thing. And here I take the example of the electron and neutrino. So the vertical line is neutrino, the horizontal line is the electron. You get the electron from the neutrino, and then if you make a rotation in this strange internal space called isospin space. So a horizontal arrow in isospin space is the electron, the vertical arrow is the neutrino. But they were supposed to be identical. Well, the electron is not identical to the neutrino, it's very, very different. One is charged, the other is neutral. Well, that's because the Higgs field in turn also takes a preferred direction in isospin space. It likes to take some direction because of spontaneous integration. So it points somewhere. And just because it points somewhere, wherever it points to, we say that the field in the same direction is now describing a particle which we call neutrino. Orthogonal to that Higgs field is the electron. If we keep that law, then finally we know how to identify electron from neutrino. And this way, it turns out, we can understand also the mass of the electron and also the mass of other particles. Without Higgs field, that is important. So the Higgs is just a way to distinguish different particles. All that was fine, but the important and subtle discovery that Peter Higgs did was that this vector might vary in length. It's impossible to keep it exactly the same length all the time. Its length might vary, and the oscillations of that length are associated again with a particle, and that was the Higgs particle. It's a very beautiful experiment done as at the International Laboratory at CERN. Many of you may have seen this picture. This is where also the whole international community contributed to making this machine. And you see it's only half ready here. The entire machine, you don't see so much anymore because it's completely filled with electronics. This also is a very, very big machine. If you look very carefully, you can see there's a human figure standing here. So this is a man standing in this machine. These big spider legs are coils that generate gigantic, strong magnetic fields, all needed to identify the particles which emerge when particles collide. You must imagine that pointing towards you will be the beam of particles, which is now in place, and right now they are under revision, but a year from now again there will run particles in there. And right in the middle of this picture, particles will collide, and the electronics which is built in here will find out what these particles do. And you get typically images of this sort, very, very complex. The particles are colliding with such an enormous amount of energy that even if you have two very simple protons collide, thousands of particles are produced in one single collision. And these thousands of particles have to be analyzed online immediately with computers, and then they have to undergo a very long series of statistical analysis, very, very difficult to finally identify whether a Higgs particle is produced. And this was successful just a year ago. And now they are consolidating the discovery to find out, is this really the Higgs particle? Does it agree with all the theoretical predictions? There's a long sequence of experiments that are still going to be done. Is this really true, or are there subtleties that we have overlooked? And we really hope that, yes, we might have overlooked the subtleties, because then life becomes interesting again. Maybe we'll learn something new from this experiment. So we want to understand the details of that Higgs particle. Now there's something else. Inside the protons and neutrons, there are subatomic particles called quarks. And those, again, obey symmetries. And they have their own peculiar symmetry patterns. The quarks were predicted, or for the first time proposed, by Murray Gell-Mann. And that is because he looked at, again, symmetry patterns in elementary particles. This is a symmetry pattern. You plot two properties of the particle. Horizontally is isospin, and vertically strangeness. I mentioned both these properties already. And there are strange and non-strange particles, and you can plot them in isospin in a diagram, and you find symmetric-looking patterns. Gell-Mann understood those patterns. He said, well, there's an elementary time in these diagrams everywhere. or triangles in both directions, actually. If you look at those triangles, you can understand that these particles they're actually complex. They are built of some more elementary units called quarks. And quarks just represent a single triangle, either this one or that one. And you can consider all these protons and neutrons as being built up of quarks. And the rule turned out to be that mesonic particles consist of a quark and another quark, and that explains their pattern. And the baryonic particles consist of 3 quarks, and that explains their pattern. Baryons can have spin 1/2 or 1.5, so 3 halves. Every quark is spin 1/2, so if it takes 3 of them together, you get angular momentum, which can go up to 3 times the angular momentum of a single quark. That's why they can get 1.5. And mesons only have spin 0 or 1. And by studying those patterns, their man could predict that quarks had to be the subunits of those particles. Quarks have been searched for a very long time without success until people realized what the forces between those quarks are. Forces, how do you compute forces? Well, you study the symmetry patterns. So physicists and mathematicians study the symmetry patterns that I have on the screen here. And they notice very strange, peculiar features, which you could only understand if you give these quarks a property which normal particles don't have. That property is nicknamed color. It is not ordinary color that you use with color vision. It is just a mathematical notion that you add to the quarks. It's a very useful notion because every quark can have 3 different colors, the basic colors, red, green, and blue. The anti-quarks have the conjugate colors, such as purple, yellow, and cyan or something. And anyways, 3 different colors. And how do you understand the forces there? Where people made a long search to understand this force, and suddenly discovered that it was the old Yang-Mills theory again. The Yang-Mills theory also explains the forces between colors and quarks. Now we take a Yang-Mills field, and now we say that the particle going through there, like a U quark, changes its color. So the Yang-Mills field doesn't affect the quark in the other way, just affects its color. And you can have, again, D quarks, and you can affect their color. So this was the discovery, and once you realize this, you can understand the forces between quarks. Except that, again, this is a non-abelian force, and the laws of these Yang-Mills fields were quite a bit more complicated than the weak interaction case. That's why it took some time for us to really understand how it all works. The theory that came out of that was called quantum chromodynamics. Chromos, the Greek word for color, and dynamics, of course, tells you that we understand now the dynamical properties of the particles. Quantum means that the quantum theory is central to this. And this allowed us to understand exactly the forces between those particles. So you might think that forces have nothing to do with symmetry. No, they have a lot to do with symmetry. Once you understand the symmetry features, you understand everything, you understand the forces. Out of this came what we now call the standard model. And the standard model grew in bits and pieces. This is a situation around 1970, and then in the early 80s, another particle was discovered, and soon enough, this happened. And now the standard model is practically complete. You might want to add the gravitational force, but that is really something that is not quite understood. I can add a name, that's easy, but to write down exact physical laws is not so easy when you add gravity. This is the pattern that we are now looking at, and from there, of course, people try to make the next step. And very soon people said, well, this is a nice pattern, let's try it, can we generalize it? And one idea was to consider the particles we have. They are colored triplets, we call them, those are quarks. The electrons and neutrinos are colored singlets, and if you take only those components which rotate to the left, then there is no neutrino that rotates to the left. So the neutrino has a component missing. So we should first start to formulate the standard theory without adding a particle that we don't see in our experiments, and try to put them in a more symmetric pattern. Maybe this is a spontaneously broken version of this picture, where they all fit together. Mathematically, well, you have to understand, because the mathematics behind all this, they put it in a particular symmetry pattern called SU5, and then they discovered you can do it better by putting things together. And then the picture becomes this, and you get, again, a more complete, unified picture of the particles. But then, of course, people saw that this hole there looks unnatural. Let's add the particle there as well. That's the wrongly rotating neutrino. When neutrinos have later been investigated in more detail, they found that indeed neutrinos can rotate in the other direction. They violate parity, but still you can have the opposite rotating neutrino. And then you have this pattern, which looks more symmetric, much more symmetric than what we had before. It is, however, repeated 3 times. So for some reason, in nature, we have 3 groups of particles. So these are all particles known today, in all matter particles known today in the physical world. So this is now all known particles put in a pattern that we can't confirm yet. We don't know whether nature really likes this pattern or not. But our mathematicians like it, and it looks that this is a more symmetric way of phrasing things, but this symmetry is rather badly broken by the forces we know. And exactly what causes the symmetry breakthrough is not yet known today. We might have to wait a very long time before all this is understood. Now I can go to some other features of particle physics, but my time is running, so I'll just briefly mention the one remaining topic of forces among particles is the gravitational force. I did mention it. What I did not yet mention is that mathematicians have great difficulty in putting the gravitational force in with the rest of the forces that are in particles. This time, again, this time we have not yet completed the story, so this is work in progress. If you have very strong gravitational fields, you have black holes. In fact, on this slide was a remark which I didn't pay too much attention to, that light charges either attract or repel. It has to do with the spin of the particle associated with the force, but I'm skipping that now. In fact, I also won't say too much about black holes. Black holes are an example where the gravitational force becomes basically infinitely strong. It becomes so strong that ordinary laws of physics have to be modified to understand what happens actually when you make a black hole. This also is a domain of theoretical physics which is not finished. But there's one very important thing, also I already mentioned this, where particles can go in and out of a black hole and they are controlled by the gravitational force. But Einstein understood that the gravitational force can be phrased by understanding that space and time are curved. So the reason why a particle may be attracted is the curvature of its space-time in which it sits. So all by itself, the particle moves into what it thinks is a straight line. But since space and time are curved, the straight lines are not straight, and the particles are being deflected. And that is the way Einstein understood the gravitational force. But what I want to say is one important thing, that gravity is also based on a symmetry. So all of laws of physics seem to be based on symmetries, or seem to have symmetries in their core, so to speak. Einstein's theory of gravity also has a symmetry built in. And that symmetry, I'll have to explain a little bit in detail what it is like. Einstein noticed that gravity can be understood by assuming space and time to have curves in them. Space and time are not flat. But that turns out to have a very important consequence. If I want to describe a space and time which are not flat, I want to indicate a point. How do I describe a point in space time that is not flat? Well, I have to use coordinates. I have to introduce three coordinates for space and one time coordinate, and then I can identify an event in space and time. So far so good, but how do you define those coordinates? Well, when a space is curved, there is a difficulty with that. So here I have a curved space, but the space on the right and the space on the left are identical. However, right and left, I chose my coordinates differently. And Einstein realized that when you formulate the laws of nature in a curved space-time, you must do it in such a way that, okay, you may introduce coordinates, but those coordinates aren't really there. There are no little lines and boxes in space and time. Those are just man-made inventions needed to identify a point on that space. But we can make those boxes in very many different ways. We should phrase the laws of nature in such a way that it doesn't matter how you choose your coordinates. Because coordinates are just man-made inventions, they're not real. So laws of physics shouldn't care about what these various coordinates are. However, we can't phrase those laws of nature without talking about coordinates. So this was a conflict situation that Einstein was in, and it took him a long time to sort things out, how to work out this theory. It took him 10 years, and then he found a complete set of equations. And the equations have the property that it doesn't matter which of the coordinates you use. You can choose any coordinate you like. Once you formulate the laws in this way, you get the same physical phenomena. This is a symmetry, because what I'm talking about, to go from left to right is a transformation. We call it a coordinate transformation. It's also a local transformation, because I can fiddle around these coordinates on one spot and leave the coordinates the same at some other spot. So this is called a local symmetry. And in this sense, Einstein's theory of gravity has a lot in common with the Young-Mills theory. In fact, Einstein's theory was discovered first, so Young and his collaborator Robert Mills were inspired by Einstein's gravity theory when they wrote down their theory of Young-Mills equations. But again, this is a symmetry, and once you understand the symmetry, once you understand the invariance, you can write down equations. So all of Einstein's laws of gravity are based on this symmetry, and that you have to understand that without symmetry, there is no understanding of laws of nature. Finally, last couple of minutes to understand all the symmetries you may have heard of. It's called supersymmetry. So how can I get to talk about symmetry without mentioning supersymmetry? Well, that's just a name that people invented because they found the symmetry to be so enormously restrictive that it's very hard to write down any physical laws that have supersymmetry respected. Yet it is also so interesting mathematically that physicists couldn't stop doing this. So what is supersymmetry? Well, you consider objects with spin. Now let me see if I can rotate, yes. So here you see two particles spinning, but they spin in a different direction. Now can I have a symmetry transformation that replaces them both? And I'll see if I can... So one particle is spinning, say, the other isn't. Can I make a transformation, replacing one by the other? And the answer is yes. That is called supersymmetry. So supersymmetry then has it that particles can spin in various ways, or they might not spin at all. So the middle particle is not spinning, the other particles are spinning. They can spin with strength 1, 1/2, 0, or spin in the other direction, and then we call it minus 1/2, minus 1. According to the ancient symmetry laws, spin remains the same. When you place a proton by a neutron in the Young-Mills theory, you don't affect its spin. But in supersymmetry, you might expect them. So bosons are particles with integer spin, fermions are particles with 1/2 or 1/2 spin. So the electrons and protons are fermions, the other particles are bosons. According to supersymmetry, you can put them into one scheme. This is called a supermultiplet. All particles are the same. It is very hard to write laws of nature that respect this symmetry, but you can do it. And that was a discovery made by quite a few people in the United States, in Holland, in Germany, at CERN. People discovered this symmetry, and they tried to write down laws of nature that respect this symmetry. And just by trying so hard, he hit upon some very interesting laws of nature. In fact, they found that yes, we can make a theory that respects this symmetry, but no, the theory doesn't seem to fit in well with what we know so far. But the important prediction is that, well, there can be, this was there's a theory that you can also involve spin 2 particles. The graviton, the gravitational particle, has spin 2, not 1. And the important discovery was that yes, you can make such a theory, but then only provided that if you add a super particle to every particle. It turned out that if you look at the existing particles which are on the column at the left, the electron, the quark, neutrino, photon, gluon, all these particles are known particles. They all figure in the standard model. None of these particles can be paired to form a supermultiplet. It didn't work. So people failed to identify any supersymmetry on the left. But if you add those particles, the superparticle of the electron is called synapton. The superparticle of the quark is called squark. The neutrino is neutrino. The photon, well, it will be a spin 1/2 particle, just like the neutrino, so we call that photino. And the gluon is a gluino, the Higgs is a Higgsino, and so on. The graviton carrying the gravitational force as a gravitino. And they all change 1/2 unit in spin. The theory is that these particles on the right should also exist. If they do, then we have supersymmetry. And this would be very interesting, because supersymmetry would resolve some difficulties that we have in the standard model today. At CERN in Geneva, there's a big search going on for supersymmetry, and they look at over 20, more like 30 different supersymmetric particles and all sorts of things, and they try to identify those particles. And today already they've excluded all these lines here. The one below is 1 tera-electron-volt, 1,000 times the mass of the proton. So they've excluded all these particles up to about 1,000 times the mass of the proton. They plan to go further to the right here, not all the way to 10, but at least to 2 or 3, when they switch on the machine at full power a year from now. So they hope to find supersymmetric particles or to exclude their existence, one of the two. I'm sure one of the two will happen, either they find the particle or they exclude that the particles exist. But that's a very important job that the LHC is supposed to do. I wish I could go on explaining you more about symmetry in particle physics. There's a lot more to tell. But of course my time is over, and so I should stop here. And I don't know whether there's time for questions or not, or for a discussion. But this is what I wanted to tell you about symmetry in elementary particles. Thank you very much.
Yes, thank you very much. Would you be willing to take some questions?
Yes, if there's time.
Are there any questions? Yes.
You gave examples where a particle travels through one of the fields whereby changes its property. But traveling through a field seems like an sort of analog property, and it's changing the property from the proton is a big change. So how do you reconcile those two views?
Well, I don't think I'll surprise you by saying that there are lots of things I didn't tell you. And one of the central features is what's called quantum mechanics. Quantum mechanics is a different kind of doctrine that you have to use to describe the subatomic particles. And in most of my other talks, I first begin explaining quantum mechanics because it's very central. But I just didn't have time. Now, quantum mechanics has it that protons and neutrons are described by wave functions. And the wave function gives you the probability that something is a proton or something is a neutron. Now, you can make a wave function which is partly proton, partly neutron, by just rotating. So this wave function is a function that continuously rotates from proton to neutron. That's why I said that isospin actually is associated to an internal space, where you make continuous rotations. So yes, the proton changes continuously into a neutron. Not the particle itself, but its wave function. That is to say, if you would measure what goes on there, the probability of measuring a proton and the probability of measuring a neutron would gradually change from certain a proton to certain a neutron.
Any other?
Yes?
At the end of the slide with the standard model, we have seen the 3 family of particles. So I know there is a E8 symmetry when they are changed to 2. Are there other symmetry like that? And what do you think about the E8 symmetry?
Well, this is a formed mathematical question. E8 is another group of symmetry transformations. It happens to be one of the most complicated symmetry transformations you can imagine. Because you can make symmetry transformations that form a regular sequence, you can make symmetry transformations that form an irregular group. E8 is the biggest irregular group of symmetry transformations you can perform among these particles. It is so far still conjectured that there is E8 symmetry. What I mentioned in the end with the grand unification, that you put all these families into these 16, 4x4 squares, there are 16 possible states there. That was a theory of SU5 or SO10. SU5 and SO10 are both subgroups of the E8 group. So E8 is still more complicated. Now, if I would be now another hour talking about supersymmetry, I would go into superstrings, which is a new theory of particles and particles at a point like a string-like. And in these superstrings, you have one of these very minor symmetries, of which E8 is a superb example of a complex symmetry, which, well, if these strings form particles in the very end, they make much bigger patterns of particles than the ones I showed here. E8 would generate a big spectrum of all sorts of particles. The particles are representations of E8. And it is possible, it's very much conjectural. String theory has done a lot to make us understand the mathematical coherence of our theories, but did rather little by way of experimental predictions. We couldn't predict anything new out of superstring theory, and E8 would predict that there would be many other particles yet to be discovered. None of those particles have yet been discovered, and I don't think that will happen very soon, because these particles would then probably have masses much, much bigger than anything that can be produced in today's particle accelerators. So the odds against actually verifying anything such as E8 in our symmetry group is remote today. And that's why I didn't touch it. I was talking more about those domains of particle physics which can be accessed experimentally. But in our imagination, we can go a lot further. In our imagination, there are only beautiful things such as E8. Well, there is a question, it was time. I don't know what you have to say.
Okay, if a brief question.
So, a brief question. You skipped the symmetry between matter and antimatter, plus sign and minus sign in front of the mass. And as you know I asked this question because in Belgium we believe this symmetry, but you in the Netherlands you don't. And I think you know what I mean.
I know what you mean, but we certainly do believe in a symmetry between particles and antiparticles. It is called C for conjugation. I mentioned mirror symmetry, which is flipping over left and right, and there's charge conjugation symmetry, yes. So if you place a proton with an antiproton, which is opposite charge, the electron by the positron also is opposite charge, that is going from a particle to the antiparticle. That's much like mirror symmetry, but now switching particles to antiparticles. Actually, neither that symmetry nor mirror symmetries are very good symmetries for the weak interactions. But the combination of two is, so if I take a mirror, but I look at an antiparticle in the mirror, then that is a nearly perfect symmetry nature, again very slightly broken. We don't know whether that's very slight breaking is due to spontaneous symmetry breaking or explicit symmetry breaking, but we do know the symmetry is not perfect. We observe violations. But then there's another symmetry if you combine that with reversal in time. So that's called T-symmetry, or PCT. Now, we cannot write down particle interactions which are not symmetric under PCT. So if I look at the particle as an antiparticle in the mirror, and then I go backwards in time, so I make a video picture and I show it backwards in time, then that's a perfect symmetry of nature that we believe is absolutely correct. There's no violation possible mathematically. Whether nature finds another way to nevertheless make it symmetry, we don't know. But what you refer to is the gravitational properties of antimatter, I think, and those, at least we all firmly believe, will be the same as the gravitational properties of matter, but not broken in a way sometimes suggested. If you break that symmetry, then all of Einstein's theory of gravity would be completely wrong. And Einstein did make mistakes, but not that big ones. And so we don't believe that he made such a big mistake in general relativity. In fact, of course, regardless of whether Einstein exists or not exists, or made a discovery or not, we now know much more about general relativity than even Einstein, and know that theory agrees with all the observations. So antimatter should behave appropriately according to gravity. So that is essentially matter antimatter. And I would turn your statement upside down, which is we all believe in that symmetry if something in Belgium.
It's a tradition to ask the keynote speaker if they would accept honorary membership in the ISA. Put you on the spot.
Put me on the spot. I didn't expect that question, but I think I can give a spontaneous answer, which is accept.
Thank you.
With honor that proposal. Thank you very much.
Thank you. Well, let's thank Chris. There is a refreshment break for about 10 minutes, so please reconvene in 10 minutes. Thank you. Thanks very much. It's best to take off the projector first.
Yes. Good.
I find that it's best to first go backwards. You turn on the projector, then you turn on the machine. So you turn off the machine, then you turn off the projector.
No, that shouldn't.
It shouldn't, but I don't know. Once I had a problem.
I did turn off the machine. I'm not sure whether I did it right in which order I did it.
We'll find out.